Hey there, Math Club. This is Noah with a Math Club video bonus. In our last episode, Key Ideas, Pete and I discussed the Diffie-Hellman Key Exchange. And one part of that was settling on an acceptable modulus and generator, which bundle together to form the public component that gets shared between the two parties. In our example, the modulus that we chose was 23. An easy way to visualize what this means is picture a circle with 0 at the top, and all of the numbers between 1 and p minus 1, which is 22, going around the circle. The generator that we're testing out is 5.
And what that means is we want to see if we can use the number 5 to generate all of the numbers that we see going around this circle here. Not the 0, but all of the numbers between 1 and p minus 1, which in this case is 22. We want to see if we take 5 to the second power, the third power, the fourth power, the fifth power. If we keep going, can we land on each one of the numbers you see here between 1 and 22? Now, of course, in most of these instances, we're going to go around the circle at least once, and in several of them, many, many times. So let's just think for a second. As we go around the circle, if we go around 5 to the second times, that will be 25, and that's going to go more than once around the circle. So what we're really interested in is the remainder, right? 5 squared, 5 to the second power is 25. If we start at 0 and go around the circle 25 steps, what it really amounts to is going around the circle one full time, and then we need to look at the remainder. So we're going to
take that generator of 5, and we're going to raise it to successive powers. Each time we're going to take our answer and divide it by our modulus. In this case, that's 23. We're going to just focus on the remainder, how much is left over after we divide by the modulus. And by taking these remainders, we want to see if we can capture every single number between 1 and 22. So let's look at 5 to the first power. 5 to the first power is 5. We divide it by our modulus. 23 goes into 5 0 times with a remainder of 5. So the 5 is the part we really want to focus on here. We want to capture that 5, and we'll show that we've got it by circling it with a token here in our diagram. Now let's add another row to our table, and now let's compute 5 to the second power. 5 to the second power is 25. 23 goes into 25 once with a remainder of 2. So let's mark that 2 on our diagram and go on to 5 to the third power. 5 to the third power is 125. Divide that by our modulus. 23 goes in 5 times with a remainder of 10. Now, I'm not going to mark that yet, because what I'd like to do now is pause here to show you a simpler way to get the same answer. We're going to use smaller numbers, and we're going to use some interesting tricks of modular arithmetic here. Notice when we look at this column, each of these subsequent powers of 5 is 5 times larger than the one before. We have 5, then 5 times 5 is 25, 25 times 5 is 125. Each one is 5 times larger than the one before, and that makes sense because we're raising each one by another power of 5. Another thing we found out here is that in modular arithmetic, with a modulus of 23, 25 is essentially the same thing as 2, because 25 amounts to going all the way around the circle one full time, and then going an extra 2 spaces. So what we can really do here, because 2 is effectively the same thing as 25, instead of multiplying 25 times 5 to get our next power here, we could just multiply 2 times 5, and we should get the same answer. Let me show you what I mean. Let's put another row here for 5 to the third power, but instead of doing 5 to the third power equals 125, we're just going to take that 2 and multiply it by 5 to get 10. Then we'll divide by our modulus. 23 goes into 10 0 times with a remainder of 10. And look at that. We got the same answer, but we got it in a much simpler way because we were using smaller numbers. And as these powers continue to accumulate, and we do 5 to the fourth, 5 to the fifth, 5 to the sixth, 5 to the seventh, you'll see it is much easier to do it this way because we're going to have much smaller numbers to work with. So let's get rid of that third row, and then let's mark our 10 on our diagram, and then we'll go on and do 5 to the fourth. Now, we're not going to actually compute 5 to the fourth. We're just going to take that 10 we just got and multiply it by another 5 to get 50. divide by our modulus of 23. 23 goes into 50 twice with a remainder of 4. And we'll mark the 4. And then we just keep going this way. We do 5 to the 5th, and 5 to the 6th, and 5 to the 7th, and the 8th, and the 9th. I'm running out of room here to add rows to my chart, but that's okay. We'll leave our red tokens on the left, but we'll clear our data on the right, and we'll keep going with 5 to the 10th, and then the 11th, the 12th, 13th, 14th, 15th, 16th, 17th, 18th. Clear another page, 19th, 20th, 21st, and 22nd. And look at that. We have captured every single remainder between 1 and p minus 1, which is 22, thereby verifying that 5 is indeed a valid generator when the modulus is 23. We hope this made it a little bit easier to understand what we were talking about in the episode, and we're looking forward to seeing you next time.